of the 13th edition does, if you have your book, you can look at it. It's a review primarily of doing integrals with U substitution, and some of them are quite tricky, which I've done on the board, as you'll see. And so this 8.1 in the 13th edition starts out with a summary, a brief table of integrals that use formulas that officially you know from Math 170. And then there are some examples, and then there are the homework problems. So if you have your 13th edition, you can look at some of the homework problems, which I have several of on the board. So let's review tricks here for doing and for finding antiderivatives. So problem one then, you see, is a U du sort of thing, because if you call this U, the du is your derivative, which gives you the 16x dx. Your du is your differential. And so you rewrite this in differential form with the new variable du over u. When it's a definite integral, you also want to change your limits so that then it's a mathematically true statement that this definite integral, which is a number, equals the same number that this definite integral gives. One of the reasons that I've tried so hard, and I've talked with you about this before now, to say that when you do have a definite integral and you're doing U substitution, you want also, as I've done here, to say, well, if x is 0, your original limit, and this is u, then u becomes, and then you put that there. And in the same way, at the upper limit, if x is 1, and if this is u, then u becomes 8 and 2, which will be 10. If you do that, then putting an equal sign between here and there is a true statement. It would be an incorrect statement to write du over u and still write the original limits. See, this number is not log u evaluated between 0 and 1, because first of all, you can't do log of 0 at all, and log of 1 would be 0, so if you wrote this equal that with the du over u, but with the original limits, you'd really be writing nonsense, you see. So that's why I'm making such a fuss about that. It's also my objection, let's say, to the My Math Lab, because you can get the answers with the My Math Lab, and you never are writing mathematics in a coherent sort of way. So anyway, this for you, then the du is certainly derivative times dx, and then the new limits are 2 to 10. So then this integral is natural log, and then you take the difference in these limits, so it's log 10 minus log 2, and then you can say the difference of the logs is the log of the quotient. So log 5 is the answer. So this is a basic U substitution type definite integral, which I'm sure you did in Math 170. This one is a good deal more tricky. It is eventually a du over u type problem, but the question is really what is going to be u? Well, if you notice, I have a recipe box over here, some recipes that are handy for this section. One of the handiest recipes is to just memorize it, really, that the derivative of the square root of x is 1 over twice the square root of x. And correspondingly, the differential would then be dx over twice the square root of x. And you use that so much one way and another that you're ahead if you learn it, and if not that, at least write it down somewhere you can find it. And so with that in mind, notice that you could factor the denominator, that your x minus root x is root x times root x minus 1. Because of course, square root of x times square root of x gives you x. So that would lead you to think, if you rewrote this factor, that you might consider calling this u, this factor, because if you do the corresponding du, the derivative of the minus 1 is 0, so the du comes from your recipe box for square root x. In other words, it's 1 over twice square root x. So that means that, except for the factor of 2, the dx over root x is du if this is u. There is if you write this as u, your du is this, so the dx over square root x, which is this other factor that's here, then is 2 du. So this is the same as 2 du over u if this is u. Okay? So thinking of it that way, then this becomes log, and if you replace the u, when it's an indefinite integral, you replace the u back to the original variable. So you have that, and then with the 2 and the rules of logarithms, you can say you have this squared. And so as a square, this is not negative. However, you cannot do log of 0, so you have to say x is not equal to 1, and you have to say x is not negative because you can't do the square root that's here. A place where the Thomas book is not quite as well written as it could be is that in problems like this, where there really are some restrictions for this word, they usually don't bother to say it. But you see, you certainly can't have x be negative because you can't do this square root. You can't have x be 0 because you can't divide here by 0. You can't have x be 1 because you can't divide by 0. Same thing. So there really are some restrictions. Stewart's book, which is what they're using now at Boise State, is better in that sort of thing. From the point of view of what a student cares about, probably it's not better. But Stewart would probably, if Stewart had this problem, he'd probably simply say x greater than 1. And then you get away from all these little picky issues that math people worry about. But anyway, this is how you do a rather tricky version of U substitution. Well, take a look at this one. If you actually have the book, you'll notice that when you get up in exponents like this, with the size of the print of the book, it takes pretty good eyesight to see for sure what it is, but I'm pretty sure it's really e to the minus cotangent z over sine square z. And this thing, even though you might not think so, is a u substitution, because if you let this be your u, then your du, the derivative of cotangent is minus cosecant square. And so that would be there, and then you have this minus sign. So the two of them together give you cosecant square, and cosecant square is 1 over sine square. So the du, which is cosecant square dz, is the same as dz over sine square, which is this factor. So if you've called this u complete with the minus sign, what you have is e to the u times du, like that. And you know how to do e to the u du. You get e to the u back again, but it's more than a little tricky, I think, to actually see that this is a u du type, u substitution with the correct du type problem. So anyway, your problem becomes this, and so your antiderivative is e to the u plus c. If it's an indefinite integral, then you're supposed to go back to the original variable, and the u was minus cotangent. So then your answer should be e to the minus cotangent plus constant.
Well, that's yours, I guess.
And so then, take a look at problem 8. This also is a little bit demanding on the eyesight, because you have the 2, the log z, and then that's a cube up on the z. And so, first of all, log of z cubed is 3 log z, right? And so you have that. And then you have 2, where the exponent is a product, and so this is the same as 2 cubed times 2 to the log z, your rules of exponents, right? And so you can say that it's 2 cubed, which is 8, then to the log z power, and rewrite it like that. And so now, if you call that the u, so that your form is 8 to the u, you notice that your du is the derivative of the log, which is the 1 over z, and the dz. So this becomes 8 to the u du, and then you have a 1/16. So let the u be log z, since this then is the du, and what you have is 1/16, 8 to the u du. And so then the question is to remember the recipe for doing the antiderivative of a to the ud. And the antiderivative for a to the ud is the a to the u back again divided by natural log a. This is in the Math 170 part of the book. Notice that it's the same thing. If you take this formula and let a become e, then your integral e to the u would be e to the u over ln of e, which is 1, and then that just gives you e to the u, which you know is right. So this is the generalization, really, of the e to the u recipe that's up here. Okay, so we have 1/16 8 to the u over log 8, and then again, when it's an indefinite integral, whatever you call u, the math department wants you to get back to whatever was the original variable. So you want to replace whatever you called u with what it replaces. So that would be log z. And so you could write it this way, 1/16 log 8 and times 8 to the log z. Okay, anybody have any questions so far on any of my u substitutions here? They are, some of them, on the tricky side. The reason that I'm doing some of these is I doubt very much that everybody here would see just what you want to call u in some of these problems. Well, let's look at 10. This is actually a u substitution, but it's, again, it's a different sort. You look at the denominator, first of all, and you would hardly see how that's going to have anything to do with a u substitution, I think, if you hadn't seen this before. Well, what you have to do is write this as a sum of squares. If you have a trinomial like this, you notice it doesn't factor itself with real numbers. You get into complex numbers, but it is a sum of squares. You can take the 2 here and split it, and take one of the 2 with the others, and you see this is a perfect square. This is x minus 1, the quantity square, and then the other one that's left is out here, and 1 is the same thing, of course, as 1 squared. So, generally speaking, you can do this kind of thing with a trinomial denominator of this sort. And now, if you call this u, then your du is dx, and what you get down here then looks like du over 1 square. You notice I turned the order around, and then what I had called u I put over here. So I have du over 1 square plus u squared. And that, perhaps you remember from Math 170, and you have the integral of, say, du over a square plus u square, it's arctangent, u over a, with a 1 over a out in front. And so having made the u substitution here, this is going to become an arctangent. Now here again with problem 10, I have the situation similar to the one that I had with this first one, that if you have a definite integral and you make a u substitution, you also have to change your limits to match the new variable so that you can actually justify saying this equals this equals this equals that, so on. Well, again, if u is x minus 1 and x is 1, then u is 0, so that's your new lower limit. And when x is 2, the u would be 2 minus 1, which is 1, so that's your new upper limit. And the 8 is just there. So my a here is 1, so 1 over a, arctangent u over a is your antiderivative for this form. And that's in that table that's a summary of integrals that's in the section 8.1. And you could also find it in the table in the back of the book. So you have 8, 1 over 1, arctangent u over 1, between 1, 0, and 1. And so you have arctangent 1 minus arctangent 0. Arctangent 1 is pi over 4, and arctangent 0 is 0. And 4 into 8 goes twice, so your answer, your bottom line is 2 pi. So this is a u substitution of a little different type, but it's actually what you're doing here. Well, I think I've covered the different tricks that are involved in doing those problems, so I think you should be able to attack them. Again, I asked this once, but various people have arrived. What we've been working with under the clock there is the 8.1 as in the 13th edition. If there's anybody who has the 12th edition and not the 13th, you don't have that section, and I copied them here. Is there anybody else now who does not have the 13th edition? If you do, if you have the 12th edition and not the 13th, you need this, and I'll give you one. I copied some here, so. Okay. So now, next we'll do integration by parts. So this is section 8.2 in the 13th edition, and it's section 8.1 in the 12th edition. Just understand that, and you have no problem, because the actual problem numbers are the same. It's all the same book. They put in this one section and raised the price $100. That's corporate America. Okay. So, integration, notice that u substitution, which we've been doing here for half an hour, is really reversing the chain rule for derivatives. Every one of these where there has been a u substitution, if you notice, if you look at whatever it is that you call u, you would have had to use the chain rule, or most of the time anyway, you would have had to use the chain rule to get the d. For example, in this one, to get from u equals square root x or square root x minus 1 to this, you're doing the derivative of the outside function, which is the square root, times by the derivative of what's under the square root sign, chain rule. Or for example, here, well, really with any of these, you're doing that. So in the same way that U substitution reverses the steps doing the chain rule derivative, integration by parts reverses the steps in doing a product rule derivative. So think about your product rule for derivatives. If you write it in differential form, you have the left hand times the differential of the right hand factor, plus you have the differential of the left times the right hand factor. And usually when we're doing this, we would turn this around and say u dv plus, put this first and that to the right, v du. So this is your product rule for the differential of a product. And now what integrating by parts does is it takes one of these terms, normally the u dv, and takes this equal this term plus that one and solves. So this is the differential of the product minus this one. And then it slaps an integral sign on, and that would be true up to plus constant, which you put on at the end. So what this rule says is that if you have an integral and you can identify the factors as u and the differential of some other factor v, you can say that it's the integral of the differential of the product, which is of course just the product, because this operation and that one cancel each other out, minus this integral over here. So the game is to hope that while you don't see the antiderivative directly for this, maybe by converting, you'll find something over here where you will see what the antiderivative is. If you can do this problem, then you could say this one is the product of the two functions that you identified as u and v to start with, minus what you get out of this integral. And this won't always help you, but a lot of times it will. After u substitution, this is the second most useful of the tricks for finding antiderivatives. I think you have already figured out that chapter 8 in your book consists of tricks for figuring out what you have the derivative of, which is what you call the antiderivative. The most basic trick is the u substitution, which you had in Math 170, and then the next most is this integrating by parts. I'm sure that right this second you don't really quite understand what I'm trying to say, but I think you will in a few minutes, because what you have to do is see some of these. It's like anything. You have to crawl before you walk, you have to walk before you run. Most of us run before we swim, although that's actually, people can swim even before they can run. You can take somebody that's 2 and you can teach them to swim. Well, anyway, we have a rule. You see, part of the problem here is, okay, what am I going to call u and what am I going to call dv? Everything in the problem that you start with has to be either u or it has to be dv. And there is this procedure which generally gives you the preference as to what to call u. So if you have a logarithm factor, that's your first choice. Call it u, and whatever else then is dv. The reason is that, you see, if what you called u over here you're going to do its derivative to form the du in the new integral that you do. When you do the derivative of log x, the logarithm disappears. You get 1 over x. It changes from logarithmic to algebraic, you see. And usually that's to your advantage. So if log is a factor, try calling that the u. If that won't work for some reason, then the next thing to try, if there is an inverse trig factor. So the I is for inverse trig, if you notice. Often with inverse trig functions, you think about what the derivative of arc sine of, say, of x is, it's, well, the derivative is 1 over the square root of 1 minus x squared. So again, you change from an inverse trig function to an algebraic type thing when you do this derivative. So that's why. Then the A is for algebraic. If you have a factor like x sine x, which I think is, I thought, well, okay, instead of x, it's t, and the example I have is t squared. But this is an example where you have a factor that's algebraic, you see. Algebraic is a power of x, or t, or whatever is your favorite letter. Okay. Then, if you don't have any of these, if it's trigonometric and exponential, usually the u will be the trig function. And then the last thing would be the exponential. Usually you leave the exponential alone because if you're thinking of e to the x, it equals its own integral and its own derivative, so you don't really change anything. Okay, so look at problem 3. This is algebraic, power of the variable, and trigonometric. So based on what I'm saying here, I should try that as u. So then you have to do your du, which is derivative times d, whatever's the letter. So in this case, it's 2t dt. Then everything else has to be dv. See, in the problem where you start, you have to account for everything. Everything is cosine dt, and therefore you can get v. Slap your integral sign on and you get sine. Now, normally you don't write plus constant at this point. The constant, if you put it down at this point, is just something, it's kind of like tripping over your own shoelaces. So we say that our antiderivative here is any antiderivative. You could choose a constant if it were convenient to do so for some clever reason, and occasionally that might happen, but normally you don't. Notice that I've set it down here. The factors must be included either with u, the factors in the original integral, either must be included either with u or else with dv, and v is any antiderivative of dv. So normally then it would be like this. So then what I'm saying is the original problem, which is the u v, u dv here is uv, where v is any antiderivative. This is the original u, minus whatever is this v goes here, du. The du is 2t dt. dt. So what I've done is convert this problem into this product minus a new integral where I've cut the power down by 1. See, the game is you cut down the power by 1 when you make u an algebraic substitution. And so I have, the original is t squared sine t minus 2 times the integral of t sine t dt. So now I play the game again. So this is a u and a dv of a different color, if you'll notice very literally. I'm doing blue and orange, not just to honor the professional football players, but also the fact to keep straight that this is a different u. Now it's t, whereas the green one was t squared. And my dv now is sine t dt instead of cosine t. And again, my v is the antiderivative of the sine, and so it's minus cosine. So my 2 integral t sine t is, this 2 is there, you see, outside of brackets. And then I have the uv here, the t and the minus cosine t, minus from the recipe, this minus, integral of the v and the du. You see, if your u is t, your du is dt. So now I get an integral to do where I no longer have this algebraic factor. And so what I'm saying is that my 2 integral of t sine t is here, minus 2t cosine t, and then I have the 2 minuses here, and so that's plus integral of cosine, which is sine. So then I have to put all this together. The original is the green and red uv, so that's down here. There's the green one and there's the red. And then out of the next time around through this, what the math department would call an iteration, then I have, from replacing the 2t sine t, I have, see, what I'm doing is, it's, at this point, it's minus the integral of 2t sine t dt. Here's 2t sine t, so I want minus that, so a minus on this makes a plus, and a minus on that makes a minus. So you get your answer down here at the bottom. And you can check your work with these, because if this is right, you could do your product rule derivatives, and if you did, it should give you what you started with. See, integration by parts is reversing the product rule in the sense that when you get to an answer, if you wanted to check that your answer is right by doing its derivative, the product rule is the rule you'd use. And that's in the same way as with u substitution. If you were to take one of these where you have the indefinite integral and you wanted to check your answer, you could take this answer, say for problem 7, and if you do the derivative, you'll be doing the chain rule, because your outside function is the exponential function, and your inside function is minus cotangent. And your derivative on this would be the outside function prime, which is your e function. So you'll have this repeated, and then times by the derivative of the inside function, which is your minus cotangent. And that derivative is the 1 over sine squared. So both of these are procedures where there is one of the basic rules for doing derivatives that you use to check your answer by differentiating backward from your answer. Okay, so then it's normal at the end of the problem to put on the plus c. So I finally do put a constant of integration on my indefinite integral, but it's at the end. It's not in the process of getting any of these v's. Okay, look at problem 5. You see that's algebraic, power of x, and logarithm. And my preference is if there's a logarithmic factor, that's the u. And you'll see this works out very nicely. So call u the log, then du is what it has to be, derivative of log times dx. Having chosen the u, everything else is dv. So x dx is dv. So then you do your antiderivative, which is a half x squared. You'd think this is taking you in the wrong direction, wouldn't you? Because you're getting a higher power for your v than you started with in the problem. But you see, even though you have to pay that price, what you get is that when you do your uv, so you have your log x and 1/2 x squared down here. When you do the VDU for the new integral, you have the 1/2 x squared right there, and the du, the logarithm has disappeared. It's dx over x. And now you can cancel that x with one of those, see the purple, and so you have a 1/2, and then you have an x dx to do. And you can do the x dx, x squared over 2. So you have a 1/2 x squared over 2 when you do this integral, and that gets you the x squared over 4. And now you put on your limits because it's a definite integral. And you see you'll have 1/2 4 log 2 minus 4 over 4 at the upper limit. The lower limit you have 1/2 log 1, which is 0, and then you have the 1/4. So 2 into 4 is 2, so you have 2 log 2 minus 1, 2 minuses make a plus. And you can call this log 4 if you like. And this would be 3/4, which is what the book has. So you see, integrating by parts, when you have a thing like x log x, works out pretty slick. And the reason, again, that you make this your choice for u is that when you do the du, the logarithm disappears entirely. And that's a big step ahead, even though the price you pay is that you convert the x dx into a half x squared. Okay, any question here on 5 or back here on 3? Follow what I'm doing. We'll drink some water and we'll continue.
supposed to either have for me today or tomorrow. Anybody need a test? Anybody got one? Okay. Let's let's look at a little maple for a minute, and then we can go on with some more of these problems. Mentioned to you, there are various computer programs that will do all kinds of math, and Maple is one of them. Mathematica is another one, and MATLAB is another one. Those, I think, are the main three now. There have been others, like so many things related to computers. There have been languages that have kind of come and gone, and makes of computers that have come and gone, and there have been some other programs. At one time, there was one called Derive that people used, and so on. So anyway, if you type capital letter INT and whatever it is, it prints the problem. You notice that the t² cosine t is this one right here. But it doesn't tell you the answer. If you type little letter INT, then you see number 2 is the answer. It doesn't bother to put on the plus constant. But other than that, you see the t² sine t, minus 2 sine t, it gave that next, and then the 2t cosine t. And why Maple gave the answer with this next and that third instead of the way that I have it, I can't answer. Maple does things like that sometimes. It doesn't always put terms in the order that you'd think. You can do definite integrals. For instance, if you were doing the integral of 1 over 4 plus x squared, which is actually the kind of problem we'll be doing tomorrow. But if you type with capital letter I, 1 over 4 plus x squared, then your limits as a definite integral, x equal minus 2 to 2, you see number 3, it displays the integral. And then you could either have typed the same thing with the little letter I, or you can type as I have with the capital I and display the problem, and then type value. And then percent sign is like ditto marks in English. They don't use the ditto marks because you use those to begin and end a string if you're writing a program. So they use the percent sign, and you get pi over 4. As I said, we'll see at the board how you do an integral by hand. That's this type dx over a squared plus x squared. You might guess it's arctangent and so on. And then number 5, I did the same thing over again with the little letter I. Okay, Maple will do derivatives, and there are 2 ways it'll do derivatives. If you have an expression, then you use DIFF, parentheses, whatever your expression is, where you're writing out the formula. An expression is where you've written out the formula in the problem. what you're doing the derivative of. The other way is you can define a function. Say, you have to give it a letter name, like f, and then for defining, it's colon and then equal, and then whatever's your variable, and then an arrow, and then your formula. If you've defined it like that, then you can use the capital letter D applied to F. So notice what I've done here. First of all, DIFF, you write your formula, sine of x, then comma, and then you have to say what you're doing the derivative with respect to. So you have to put the x, and you get cosine. That's number 6. Or if you do DIFF sine x, x dollars sine 5, that's getting you the 5th derivative without showing all the steps in between. That would be very handy if you had some expression and you wanted some high order derivative. You don't, if you had Maple or MATLAB or Mathematica, you can just say what order derivative you want, you see. Then with 8, I'm redoing this by defining sine as a function. So you see the letter F is my name for my function, the colon, and then equal, and then the variable, and then the arrow. You use the minus sign and then the angle bracket on the keyboard. So one problem you have with getting a computer system to do math is all the keyboarding to get it entered. And of course, that's a problem you have with the MyMathLab type homework and so on. So anyway, I've defined f as sine x. See, that's line 8. Then if you've defined the function, just use capital D for the derivative. Maple reserves the letter capital D for derivative, and it won't let you do anything else with it other than just typing text or something. So D applied at F, applied at X. You see how the parentheses go. And that gets your cosine. And then if you want the 5th derivative, if you want a higher order derivative, you use the double at sign. So D at sign 5 applied at F. So 10 is the same thing as 7. There is the dollar sign 5. And then the 3rd derivative, you see, is number 11. And 12 is done the same way with the DIFF. Okay. There's more Maple there, but I think this is enough of the Maple for today, but I'll talk about the rest of the Maple that's in this handout, so bring this one back. We can talk some more about it tomorrow. Meanwhile, let's do the rest of these problems. So here's x e to the x. Again, you see, you don't have a log, you don't have an inverse trig function. So going across here in order, what should be the dv? The first thing that, or what should be the u rather, is the algebraic power of x. So let u be x, and then the du is dx. Once you've chosen u, everything else is dv. So you have e to the x dx, so v is e to the x, any antiderivative. So then you have uv minus v, which is the e to the x, du. And then that integral you can do easily. That's e to the x.
So your answer is x e to the x minus e to the x plus constant. And here again, if you wanted to take your answer and do its derivative to get back to there, you'd be using the product rule to check your work. It's in that sense that integrating by parts is reversing your steps on the product rule. Okay, take a look at 12. Well, again, no logarithm, but you got an inverse trig function, right? So that's going to be the u, and what's left over is dv. So you have to go look in the book probably to remind yourself how you do the derivative of the arc sine, but it's on that summary page that's at the start of 8.1 in the 13th edition. So you'll find maybe it's a different letter from y, but whatever the letter, say an x, it's dx over square root of 1 minus x squared. So that's your du, and then of course the v is y. So then you have uv, y arc sine, minus the integral of v du. Okay, so this one now is something that you can do. This becomes y dy over the square root. This is a u substitution. So I'm using the letter u in a different sense now. This u is not that one, which is part of the integration by parts recipe. This is the u substitution recipe, different color. So if that's the u, then you notice that the minus 1/2, if u is 1 minus y squared, du is minus 2y dy. So the y dy, which is what you have here, is minus 1/2 du. So this is a u substitution, u to the minus 1/2 times minus 1/2 du. So you can take the minus 1/2 out, and you have u to the minus 1/2 du. So you add 1 for the new exponent and divide by that. You cancel this 2 with that, and you have minus the square root u, which is, this minus is there, and the u is your 1 minus y squared, and this minus is the one from here, the uv minus v du. So there are two minuses there to make a plus, and so you have the square root plus the y arc sine. And you notice if you were checking your work, you would have to use the chain rule to do this derivative and product rule to do that one. And if you did it right, it ought to get you back to what you started with. Okay, so the last type of thing that we have is number 21, which we'll do in just a second. I want to get my side. Well, what you do with this type, it's partly calculus and it's partly algebra. It's a little different game on integrating by parts. So first of all, you look at what you're starting with, and you have trigonometric and exponential. So it's just those two. So presumably then your e to the theta, d theta is the dv, and your sine is the u.
and then your du is cosine d theta. And this being dv, then the v is e to the theta. So you have uv minus the integral of v du. So you've converted from the integral of e to the sine, or e to the theta sine theta, pardon me, into e to the theta cosine theta. And the game is that if you will do this again, you'll get back to something that's e to the theta sine theta, and then you can solve for it. The reason is that sine and cosine have the property that they are each other's integral and each other's derivative, except for a change from plus to minus, right? If you do the derivative of cosine, you get sine back again with a negative on it. So if you play the game on this, see, what you have to start with is the original is this product minus this. Now in this, do a u and a v of a different color. So in the integral then, the u is your trig function, and the du is what you get, which is minus sine d theta, and then the dv is the e to the theta d theta, so the v is e to the theta. Okay, so now this one here that I'm working with, the integral e to the theta cosine theta, is its uv, e to the theta cosine theta, minus the v du, and so I have integral e to the theta cosine theta is e to the theta cosine theta plus this integral. Notice that this integral back again is where we started, up here, and it will be on the opposite side of the equal. See, if you put this together, here's where you started. That's this. First time out with the red and the green, you got it equal to e to the theta sine theta, that's that one, minus this integral, which is still red and green. Okay, so I'm copying this, and I'm copying this, and copying the minus. Now I'm replacing this integral with what's inside of the brackets. You see, it's from down here, it's my uv minus the integral of v du. And so the original is this minus on this, and then this minus on that. So now I have the original equals product minus a different product minus the same thing. So I can take this to the other side as an unknown. See, it's like a problem where you're to solve for x. X, that's x, equals e to the theta sine theta minus e to the theta cosine theta minus this same x. So as an algebra student, solve for x means add x to both sides. And so you have 2x equals this minus that. So you have 2 times the integral you want. And I can factor the e to the theta there. So the integral you want is this factor over 2 times this. So you do get something which, if you do its derivative using the product rule, will check and give you that. And you see, you've done it partly by doing integrals and partly by seeing that you get the equivalent of this algebra problem. And that's where this is a different game from the others. The others don't have this game where your integrals take you to an equation where your integral that you want is like an unknown on both sides of the equation, but with an opposite sign, so you can solve for it. Well, I think that's a board full for today. And what we'll do tomorrow in the section 8.3 of the 13th edition, which is 8.2 of the 12th edition, is the kind of thing that I mentioned with the maple, how to do the integral of something like du over a square plus u square, such problems. They're all trig substitution, as you'll see tomorrow. So if you have the test finished, I'll take it. If you don't,